All right, let's start. So the problem we are going to be dealing with is point location problem, and this is really practical applications like locating a point on a map efficiently, and also I mean the main application will be in the maps. And given a point, can you find which city this point is contained in quickly? And we are given a point, a query point P, and we are given a planar subdivision as a doubly connected edge list, for example. So we have, we are going to assume that our planar subdivision is bounded this time. We have a large rectangle R which bounds our map, and this, as you remember, we have edges in this, so there and there they correspond to faces. Okay, so something like this. So given a planar subdivision like this, let's have another one here, and given a point P here, can we find the face that contains this P quickly? First, I'm going to describe the search idea. What we can do is, and we are going to make certain assumptions initially so that the algorithm runs correctly. The data structure I'm going to describe, we are going to make certain assumptions. But first, without making these assumptions, assume you draw by looking at, so your planar subdivision is maybe also given to you, not as a doubly connected edges. We are going to, we can convert this problem to a set of edges. So by just looking at these set of edges, they may have shared endpoints, but as you can see, these line segments, they do not intersect with each other. Okay, we do not have edges intersecting with each other. If they were intersecting, there would be a vertex at that point, and they will be 4 separate edges. Okay, so in a doubly connected edge list, the edges do not intersect with each other. So that's one assumption. We are given non-intersecting, but possibly they may share some endpoints. But they are not intersecting in their interiors. So we are given such n line segments, and we are trying to locate this point P. So the search is based on this idea. First, imagine you draw vertical line segments, vertical line segments within this rectangle R that pass through. Do I have another color? That pass through, for example, we have the left edge, we have this one, that pass through the x coordinates of all endpoints. So if we have n segments, we are going to have 2n endpoints, left and right endpoints, and we are going to draw vertical lines that pass through all these x coordinates. Okay, so in order to find this is going to give us vertical slabs. So we divide our region by using these vertical slabs. We divide it into these regions, and P is going to be contained in one of these vertical slabs. And if you conduct a search on the if you have again a binary search tree on the x coordinates, you can find in log n time which vertical slab the P is going to be contained in. But you are going to know it's going to be contained in this vertical slab, but you don't know yet which face. It can be here, here, here, here, or here. Now, if we look at these vertical slabs, we see that there is no vertex contained in a vertical, within a vertical slab. There is no vertex because we drove vertical lines with these endpoints, so there would be 2 different vertical slabs. So there's, when we look at a vertical slab, we see that they look like trapezoids, okay, or possibly rectangles. If there's the left, so each within this vertical slab, what we have now, let's try to analyze a vertical slab. It's going to be a set of line segments intersecting the vertical slab. Some of them may have this vertical slab in their interior. Some of them may have it, may intersect this vertical slab by their left hand point, and some of them by their right hand point. It may be something like this. It may be something like that as well. So, but here, what is apparent is that there is an ordering. These segments, this intersection of these segments with this vertical slab gives us a way to order these faces from top to bottom. Okay, so I mean, based on given a query point Q, if we also know, if we can conduct a binary search on these slabs. For example, by selecting this one, we say, is our query point at upper or lower with respect to, is it above this segment or below that segment? If it's above this segment, we can continue our search on the next segment in a similar to binary search fashion. We can locate this which face P is going to be located in. So we first conduct the search on the x coordinate like this, which is log n, and then we conduct another search on these segments that intersect this vertical slab. If we know these segments, if we know an ordering of these segments intersecting this vertical slab, what we can do is we can do again a binary search on the whether it's above or below a given segment. We can check whether P is above or below a given segment Si within this slab. And at the end, this will be another log n time query. So the total query time is going to be log n plus log n, log n. Okay, so in all log n time, we can locate the face that contains P. Now, the rest of the chapter 6 is all about, I mean, we are not going to try to reduce this log n time complexity. Okay, so at the end we are going to be happy with our query time. Log n query time is okay. We are good with this. But the rest of the chapter is dedicated to the space complexity. Okay, so what kind of a data structure do you need? So look at this vertical slab data structure. We need, for each slab, we need to sort the segments. We need to have a binary search tree on these segments for each vertical slab. And what is the space complexity of such a subdivision which has these vertical slabs? So we are going to see that the worst case, actually I can directly draw a possible worst case, which may contain n square segments. So the complexity is going to be bounded. The space complexity is going to be bounded by, after you draw these vertical lines, the new subdivision, how many faces it can possibly contain. Okay, so this is the question we are going to ask. The intersection of these vertical segments with the original subdivision. If you are intersecting 2n vertical segments with possibly an on number of faces. If you have n edges, the number of faces is also limited by on. But if you intersect these two things, what can be the how many trapezoids like can you have at the end? What is the maximum number of faces? These smaller faces you can have after you intersect these vertical slabs with the original subdivision. And if we use this approach, we are going to see that we can sometimes end up with O(n) square faces. And here's an example. This is how I arrange my line segments. So my faces, So these are my segments. Let me try to be, yeah. And there are some line segments like this. So if I can have n over 4 endpoints here, n over 4 endpoints here. So the reason I drove these vertices in the middle is since I'm going to draw a vertical slab from each vertex, I'm going to have these vertical slabs like this. It means that I have n over 4 times, at the end it's going to be n over 4 times n over 4 possible small regions here in the new subdivision. So this is a possible worst case arrangement of an original subdivision. So if you draw these vertical lines, you may at the end up with many on the order of O(n) square smaller regions that you may need to search for. Although, for example, a point here is trivially can be found by just conducting not first on the x coordinate. If you just conducted a search on the y coordinate first, maybe if your slabs were horizontal, you would maybe need much less space in terms of it's not going to be n over 4 times n over 4, but it's going to be on the order of O(n) possibly if you've chosen a different way to draw these slabs. Now, do you understand how we conduct is it clear how we conduct the search and why we can possibly have the space complexity can possibly be quadratic in this worst case, for example, we can reach the quadratic complexity. And here, when I say complexity again, I'm trying to bound the number of faces of the region overlay of these vertical slabs with the vertical lines with the original subdivision. Because at the end, what we will be constructing is that we are going to have binary search trees for segments at each vertical slab. Okay, so the total space complexity is going to be this binary search tree, this binary search tree, this binary search tree. So at the end, it's going to end up the space complexity of this one is the number of trees here. Okay, if it can be O(n), if I have O(n) of these trees, it's going to be O(n) times O(n) times O(n), and n of them is going to be O(n) squared. The summation can be O(n) squared at the end. So we are having if we can bound the number of if we can have a better strategy instead of drawing these vertical slabs that go all the way up and down. The trapezoidal map is going to reduce the space complexity to O(n) with a better strategy. So, and we are going to see it next. Yes. Oh, okay. So very good. We can actually. So this is a very good idea. Why don't we use something like a plane sweep, based approach to even locate this P or to create a structure, for example, suitable for answering such queries. We could do that actually. We could do a plane sweep approach, but it's an alternative. A plane sweep based approach can be done, but we are going to let's first decide on the data structure. Okay, what kind of a the index structure you are going to have. What you are saying is that without having any data structure, just the original subdivision, can we locate P using some kind of a plane sweep approach?
Sonuçta bütün şeyi tek location'ları bilmemize gerek olmayabilir. İçinde bulunduğu x aralığındaki ufak kareleri bilmemiz yeterli değil mi? Hani Ya sonuçta ikisi
Yes,
de-
exactly, exactly, exactly. So this is why it takes log n time. So this is, I mean, first you need to determine the interval which the line segments which are possibly within this slab. I mean you know the x coordinate and y coordinate of P. By looking at this x coordinate, you look at the x coordinates of all the segments to determine which are within this, which contain P in their x intervals. Okay, so and this can be done in log n time. And after you do that, okay, do we really need, do we really need a data structure? Okay, just by just looking at the segments, do we really need an extra data structure to perform this query? This is your question. Maybe by just having this line segments and line segments, can we perform this query fast? Let's think about that.
Ya benim aklıma aşağıdan yukarıya place sweep yaparsak just yani sağındaki ve solundakileri bulduktan sonra hani hemen sağındaki ve hemen solundaki.
Okay, so in order to do plane sweep, okay, we can do that, but we cannot. This plane sweep is not going to guarantee n log n log n complexity. It's going to be n log n. First, we need to sort the points. Okay. We need to sort the line. We need to sort the points, but assume this is our data structure, the sorted set of lines, the sorted line segments with their. I mean, sorting the endpoints of the line segments with respect to their x coordinates. Again, this is ON space. Imagine we constructed this in n log n time. And it takes ON space, just storing the n segments. Now, we can locate, but this is not strictly a binary search tree. We still need to. There may be multiple segments within the same interval, so we still need to be careful about how to store these line segments. So it's not that trivial. It's not just endpoints. I mean, at the end, we need to, for each endpoint, we need a set of segments within that interval, and then it turns out to be the same as these having vertical slab thing. Okay, what we need is for each x interval, a beginning and x interval, we need the line segments, all the line segments within this interval, right? In order to perform this query, we need all the line segments with, for example, between x is equal to 5 and 10. Okay, if we know that, or not x is equal to 5 and 10, if we know the xy coordinate of this one, if we have the sorted endpoints, what we find at the end is all the line segments that contain this x within their left and right endpoints. Okay, and it corresponds to finding this vertical slab. And there may be possibly, and this worst case tells you, what this tells you is that there may be possibly n line segments, n over 4 line segments that contain P in their interval. Okay, and the next thing is you conduct a search on the order. You can order these line segments, but these ordering, in order to have these orders for each interval, you need a different order. The order of these line segments within this interval may be different at the next, okay? Or the set may change. So for each vertical slab, you need sorted segments in order to perform this query. So it then turns out to be, if there are ON such, you need to store such ON, possibly ON line segments for each interval in order to, if you are going to perform this query frequently. If you are doing this only for one point, you are not going to need ON square storage, because after you find these line segments within this interval, you just build a binary search tree on these possibly ON intervals, and you perform your query. So if you're just going to perform one query, you don't need ON square space. But what if at the next query, I query something here. So you need another binary search tree for this here. So in order to perform multiple queries in different locations, at the end you will end up having binary search trees for each vertical slab, and there are possibly n of these vertical slabs and n segments in each of them, and it turns out you have O(n) square storage at the end. Now, I'm going to now define another data structure, which is going to have reduced amount of storage, and it's based on the fact that do we really need to extend these vertical segments all the way up to this point and this point. Here, in trapezoidal maps, we are not going to extend these vertical segments all the way up. We are going to do this. Let me just erase the whole thing. And subdivision. So imagine I have this map, planar subdivision. Now, in the original approach, what we were doing was we were extending, for example, for this x coordinate, we were extending all vertical line all the way up and down. Now, in a trapezoidal map, what we are going to do is we are going to extend these vertical segments from a vertex Q. I'm going to extend this segment until it intersects an existing a segment of a line segment of the subdivision. So the extension is going to end here. So let's do it for every vertex. This is going to end here. This is going to end here. So each vertex has an upper extension and lower extension segment, and they end. We stop extending these segments as soon as we hit a line segment of the subdivision. Okay, so this becomes our trapezoidal map. Okay, the only difference, as I repeat, is that we don't extend these vertical segments all the way up and down. We just stop whenever we hit one segment. Okay, so if we look at this trapezoidal map, we see that here, for example, look at this case. This trapezoid here may have two upper neighbors. Okay, it's not, now we are not talking about single vertical slabs. Vertical slabs do not exist anymore in this representation. For example, here, this vertical slab is divided into three, and then it disappears here. There's a trapezoid here. So some trapezoids merge. I mean, look at these. And sometimes the trapezoid, if for these trapezoids, we talk about four edges of these trapezoids: the upper edge, lower edge, left side, and the right side. And sometimes the left side may converge at a single point, so it becomes a triangle. Okay, or the right side may converge at a point. So, for example, here the right side converges at a point, and this trapezoid becomes a. So this is the upper edge, lower edge, left edge, and the right edge, which is just a point here. In that case, it's a triangle. We have another triangle here. But in general, they look more like trapezoids. So even you can think about the triangle as a degenerate trapezoid with one edge 0 length. Okay, so that's why these maps are called trapezoidal maps. Okay, now we perform the query in a similar fashion. Each x coordinate, by first conducting a search on the x coordinate, we find the region, for example, this is here. Each of these vertical slabs, actually, let's look at the query algorithm. Actually, I mean, we perform the same query on the trapezoidal map. Okay, the query algorithm is no different. We first, I mean, our goal now will be to find out which trapezoid includes this point P. So given a query point P, the question becomes which trapezoid. So we are going to have a number of trapezoids in this trapezoidal map. The goal will be to find which trapezoid this P is contained in. And since we have the endpoints sorted, we can find again the possible trapezoids within this slab, and each of these trapezoids are again sorted, can be found by sorting them, and again the log n time search can be performed in the same manner in this trapezoidal map. Now, the thing we need to find in this trapezoidal map is how many trapezoids this contains. So in this worst case, we could have n square faces, but with this new approach, what is the number of trapezoids, the possible trapezoids? Is it a linear structure or n log n, or is it still n square? So the next thing we need to do is prove that it has that many trapezoids, and here is the way to prove that. So we are going to consider all these different. Let's consider. Let me go with the same structure as the book. In order for this trapezoidal map, in order for the time complexity to work correctly, we are going to make some additional assumptions, which is this assumption is going to be a very big assumption. It's going to seem like a big assumption at first, but your next assignment for next week is going to show that actually this is not a big assumption. It's about getting rid of this assumption. And I'm going to tell you the solution. So the assumption is that no two endpoints have the same x coordinate. Okay, so we are going to have, for example, this x coordinate. We are not going to have another x coordinate at the same x. So each x is used by a unique endpoint. We are going to, so there is no x coordinate at the same x, there is no endpoint at the same x coordinate. So we are going to need this assumption to bound the space complexity of the trapezoidal map. But this assumption, having no two x coordinates, no two endpoints at the same coordinate, can be gotten rid of easily by actually slightly transforming this endpoints with a shear transform. Okay, imagine just if you had points, multiple points at the same x coordinate, and you're unable to sort them with respect to x coordinate. The shear transform, what it does is, this is what shear transform does. Given an x point xy, it transforms it to x plus some epsilon y and y. So this transformation, what it tells you is that their y coordinates will not be changed, but based on their height, based on their y coordinate, I'm going to change their x coordinates. So the points are going to be, so this is going to be slightly here, this is going to be slightly here, and this is going to, so after they're transformed, what happens is that no two endpoints will have the same x coordinates. Okay, so this shear transformation is going to modify the points, is going to, if we apply this transformation, no two points will have, so these are going to be my new points. As you can see, no two of them have the same x coordinate. But the problem is, if this epsilon is too big, the original order may also be, you also have other x points here, okay? For example, there's another x here. There were points with different x coordinates originally. So while you are doing this shear transform, this epsilon cannot be too large, because otherwise a point that was, for example, look at these 2 points. The x coordinate of this is smaller than this. Okay, let's have it here. So look at these points, x1 and x2, x2, y2, x1, y1. If the shear transform is too big, this point, which was to the left of this point originally, may go, after the shear transform, it may appear to the right of this point. So you cannot have too large epsilon. You don't want to disrupt the original order of unequal x coordinates. But if they have equal x coordinates, you want to disrupt their order. You want this one, the upper one, to be to the right of the lower one. But if the points were originally different, if they had originally different x coordinates, you don't want to disrupt this order. After this shear transform, this should still be smaller than the other point. So your assignment for next week is that given a set P of n points, given n points in the plane, with some of them equal x coordinates and some of them different x coordinates, how can you find epsilon so that when you perform this transformation, epsilon should be greater than 0. If it's greater than 0, you are going to ensure that equal x coordinates are going to be different now. If epsilon is greater than 0. If epsilon is equal to 0, it means that you're not doing any change. The transformation is not doing anything. But if finding an epsilon greater than 0, which is not going to disrupt the original order of the unequal x coordinates. Okay, so how can you find, what is the maximum epsilon which guarantees you that you are going to change, so you are going to find a maximum such epsilon. I mean, you can say a trivial solution is that given epsilon, for example, 10 to the minus 20, for example, a very small number, is probably going to guarantee that these are changed and disrupts nothing. But even 10 to the minus 20, I can give you a certain case, it can even disrupt the order of this. I mean, if I give you the difference between these two, to be 10 to the minus 21, for example, in terms of x, this shear transform is going to modify their order. So you cannot determine this epsilon in a fixed manner. You need to look at the original x coordinates of the points. So your goal in this assignment is find an ON log n algorithm to find this epsilon. You are going to find an epsilon which is going to help you to reorder points with the same x coordinate without modifying the original order of points with different x coordinates. Yes?
Original order değiştirmesek de noktanın bulunduğu yer değişebilir mi? Nokta başka bir face.
Oh, okay. Without changing the no, actually the faces are already determined. I mean, these are the points which determine the faces. Okay, so the faces are going to be distorted. The faces are going to change their shapes. But the point itself does not go to a different shape. I mean, these are the points define the shape. These are not query points. These are the endpoints of the shapes. So your shapes are going to be distorted, but the distortion should not be that much so that the shape, for example, if the upper endpoint of the shape was to the right of the lower endpoint of that edge, it should still be like that. I mean, we don't want to change the order of the shape. That's the main constraint. And in real implementation, actually, we don't need to really perform this shear transform to get rid of this assumption. This comparison can be, I mean, this shear transform can be done symbolically, meaning that without actually performing this transform, when you have equal x coordinates, you also look at their y coordinates to determine an order. So it's like you don't need to really transform them when you are implementing the algorithm. This is called symbolic manipulation of points to get rid of this assumption. But now, for the rest of this class, since we know how to get rid of this assumption, now we can safely continue our discussion by assuming that no two x coordinates, no two endpoints have the same x coordinates. Okay, so the rest of the discussion of trapezoidal maps, we are going to make this assumption that no two endpoints have the same x coordinate. Now, so this is the first thing that we prove is that with these two assumptions, any face, each face in a trapezoidal map, so this is lemma 6.1 in the book, with this assumption that no two endpoints have the same x coordinate, we can now say that, I mean, I already told you that they look like trapezoids, but this is actually a lemma. We need to prove that. With this vertical, lower and upper vertical extension, do we guarantee really each face at the end is going to be a trapezoid? And this is what lemma 6.1 says. It says that each face in this trapezoidal map of a set of n line segments has one or two vertical sides and exactly two non-vertical sides. Okay, so it's either a triangle or a trapezoid with four sides, to left and right side and up and down sides. So each of these trapezoids can be represented by four edges. If we didn't have this assumption, a face may contain two left edges, as you can see here. If we didn't have this assumption, we may have multiples. So actually there's a worse example here. We could have something like that. A trapezoid, so it's a better example. Let me show you that. Imagine line segments like this. They all have the same x coordinates, and these are their vertical extensions. And I may have a trapezoid here with more than one left neighbor, more than one left edge. Okay, it says these are all separate edges. Since these are vertices, since I have vertices here, okay, since these are vertices, this is not a single edge. Although it's collinear, these are all different edges. So if we don't have the assumption that no two endpoints have the same x coordinate, we could end up having a trapezoid having more than one left edge. But with that assumption, when we perform this shear transformation, we are going to have different, with these vertical slabs, we are going to have different trapezoids. And therefore, we can only have actually 5 cases. Okay, so it's either each face in this trapezoidal map is going to be, going to be a convex shape. It's going to be convex, and it's going to have at most 4 sides, up, down, left, right. And one of the left or right sides maybe a point. Okay, in that case, it's going to be a triangle. At the same time, they cannot be both points. It's going to be a degenerate. It's not going to be a face of the trapezoid. It's going to be an edge of the trapezoid. Trapezoidal map. Okay. So here is, now let's look at the next thing we are going to do is, we are going to look at more properties of this trapezoidal map, how each trapezoid looks like. And the next algorithm that I'm going to describe is going to be a randomized incremental algorithm to build this map. How do we, so we are given a set of line segments, non-intersecting line segments in general position, and general position indicates our assumption that no two endpoints have the same x coordinate. This is what general position means. No two endpoints have the same x coordinate. So given a set of line segments, how do we construct a trapezoidal map of these line segments? And our randomized incremental algorithm is going to insert each line segment one by one and construct the trapezoidal map incrementally. Okay, so we are going to construct this map, and the invariant of this construction algorithm will be if we process the first I line segments, the trapezoidal map for these line segments is a valid trapezoidal map. So when we add a new line segment, we are going to update the trapezoidal map accordingly, and it's going to be again another valid trapezoidal map. Okay, so here are okay, so these are the, for each trapezoid, let me there are 5 cases for the left side of it. So just take a trapezoid in this map. There are 5 cases about how the left edge of this trapezoid is going to appear. Okay, so it can be, it either degenerates to a point. Okay, so this is the left side can be a point, and so this is our trapezoid. This is our vertical extension, and we indicate the segment directly above this trapezoid as top delta, and bottom delta indicates the segment immediately, the segment that determines the lower edge, bottom edge of the trapezoid. So this is case 1, case 2, and similar to this one, we have, so this is again bottom trapezoid. This is my trapezoid. We have this upper extension this time, and the top edge of this trapezoid. And also we can have both segments okay, still we have this another segment that ends here. Okay, so I mean here in this case it has 2 edges on the left, so it doesn't have, but both of these 2 edges are defined by a single vertex. Okay, still by knowing the single endpoint, we can generate the left side of the trapezoid. We don't need more than one endpoint. So there are the left side can either be both the lower and upper extension of a independent segment S like this, or it may be the endpoint of the bottom segment or the endpoint of the top segment, or both segments can emerge at the same point. The 5th case is the case where the left side of the trapezoid is the left side of this big rectangle R. So for the two trapezoids that appear leftmost and rightmost, their left and right is defined by the rectangle, the big rectangle R. So we ignore these cases in the general analysis. Okay, so in order to, the reason that I am telling these cases is that how do we represent a trapezoidal map? What do we need? Which information do we need to represent each trapezoid? Okay, so all we need is that each trapezoid can be uniquely determined if we know its top segment, bottom segment, and its left trapezoid and its left point and right point. So, and the left point and right point are defined as the left end point of top or bottom, or it's the right point of the third segment. So here, this point here is defined as the left point of the trapezoidal map. Okay, it can be either the left end point of top or left end point of the bottom segment, or it can be the right end point. So this is still left P trapezoid, or it can be the right end point of a third segment S. Okay, so given these two segments and this point, and similarly the same thing for the right part, this point on the left and this point on the right. So given 2 points and 2 segments, each trapezoid can be uniquely identified. Okay, so in order to identify trapezoid, we need these 4 things. Now, and the next thing that we are going to prove is that with this, since we have these 4 things, we know how many trapezoids we can have at most. Okay, since we said that each trapezoid is uniquely identified by 2 segments and 2 points, and it turns out that trapezoidal map is going to contain at most 6n plus 4 vertices. So a trapezoidal map contains at most 6n plus 4 vertices, where n is the number of line segments that define this subdivision. Okay, and these come from the fact that the vertices, since every point, since we have 2n endpoints, okay, we have 2n endpoints. Let's look at the vertices. How many vertices we can have in this trapezoidal map? So these are going to be vertices. So this is going to be a vertex. This is going to be a vertex, vertex. So here, what we do is we have 2n endpoints, and we have also 4 vertices here. Okay, the 4 vertices of R. Okay, it's going to be 4 plus the vertices themselves, okay, and plus each of these, for each of these endpoints, we have 2 extensions, lower and upper, and each of them can introduce 2 new vertices. So and it's going to be 2 plus 2 times 2n, which is going to be at the end 6n plus 4 vertices. Okay, so for each endpoint can introduce 2 new vertices because we end their extension as soon as they intersect the segment. So each of these 2n endpoints can introduce 2 new vertices. So this is the upper bound. Sometimes they may also end up another vertex. They may share a vertex. So this is the number of vertices that may be potentially induced by the lower and upper extensions. These are the endpoints of these are the existing number of vertices, and the 4 vertices introduced by this rectangle R. So a total of 6n plus 4 vertices may occur in this trapezoidal map. And by using the Euler theorem, we can say that if a subdivision has this many vertices, the number of edges, the number of faces can also be determined by these vertices. This many vertices can have at most 3n plus 1 faces, okay, using the Euler theorem. It turns out that the number of trapezoids we are going to have at the end is going to be linear. I mean, by just looking at the vertices themselves, you can find that you cannot have more than linear number of trapezoids at the end. So what this shows is that by using a map like this, we can have a linear storage. We avoid now ON square. The initially ON square storage to do this query is now reduced to ON storage. So if we can build this trapezoidal map, we are going to have an efficient data structure for our queries, which is in linear space complexity. Okay, so this is the end of introduction to trapezoidal maps. Let's have another 10-minute break, and I'm going to describe a randomized incremental algorithm, which expected n log n time complexity. I think let's see, the expected running time of this algorithm is going to be n log n. So in n log n time, we'll be able to create this trapezoidal map, and it's going to have an expected size of ON. It's going to have a size of ON, and we'll be able to build it in n log n time.